bounded by this, that is x squared plus y squared equal to 4, bounded by this, and also bounded by z equal to 3 surface. So z equal to 3 surface here is the top surface here. So you assume that there is a flat surface cutting the infinite cylinder. So now that we have one surface here called S1. S1 is the bottom surface. Another surface here called the S2, that is the top surface here. S2, the top surface here. The equation for such surface is z equal to 3, because for every point here the surface, the z value is 3. And we have another curved surface which is defined by this equation of a cylinder or equation of a circle, x squared plus y squared equal to 4. So you have a curved surface here, circular curved surface here. For every point on the curved surface, x squared plus y squared equal to 4 is the equation defining any point on the curved surface here. Okay, so as you can see in this picture here, you now have a closed surface. The closed surface consisting of S1, which is defined by z equal to 0, and S2, the top, that is defined by z equal to 3, and a curved surface S3, which is defined by x squared plus y squared equal to 4. So you see that there is a closed surface here. Now within this closed surface, we assume that the vector A is defined. The vector of A is a valid vector field within this surface. Then we will verify the divergence theorem. So in order to verify divergence theorem, we have the left hand side of divergence theorem, which says that the volume integration of divergence of A is equal to the right hand side, that is the surface integration of the vector field A, or the flux, the total flux across the vector field A. Sorry, the total flux of the vector field across the closed surface. So keep in mind that you can now see that there are three sections in the surface here. S1, the bottom circular surface, S2, the top circular surface, which are flat surface. Passing for that, the equation of the plane is z is equal to 3. For any point on the top surface, z value is 3. For any point on the bottom surface, z value is 0. And for any point on the curved surface here, on the edge here, on the side surface here, the equation is x squared plus y squared equal to 4. Now, in order to verify divergence theorem, we'll start with the left hand side here. The left hand side is volume integration of divergence of A. So you just take the divergence of A. Divergence of A, as I already said, this is the del operator dot product with the vector A. Del operator is I del upon del x plus j upon del y. All these partial derivatives operator dot product with this vector A. So this is quite simple. I dot I is 1. I dot j is 0, I dot k is 0. Therefore, what we have is del 4x upon del x. So 4 is a constant, so it will be del x upon del x. So the first term will be 4 only. Now the second term is j dot j is 1, j dot I is 0, j dot k is 0. So when you differentiate minus of 2y square here with respect to y, then you will get minus of 2 into 2y, that is 4y, minus of 4y. And similarly here you will get differentiation of z square as 2z. I think everybody knows this. Now the next part is where we perform the volume integration here. So volume integration of divergence of A, we already know that this is divergence of A. Then we have to perform volume integration. So as I said, if we define this system using what is called Cartesian system like x, y, z here, any infinitesimally small volume element will be written as dx, dy, dz. The product of dx, dy, dz. What is dx? Small increment along x-axis. What is dy? Small increment along the y-axis. dz is small increment along the z-axis. So the small increment along each of these coordinates, if you multiply these things, you will get what is known as the volume element. Now, in order to cover the whole volume as defined in the question, you have to choose the limit of integration. So what is the limit of integration we have to choose? Let us first start with z integration. Z integration is quite simple. In order to cover the whole volume as enclosed by this surface, in order to cover the whole volume as enclosed by this surface, you assume that there is a volume element called dx, dy, dz here within this volume. So we have to cover the whole volume, means you have to sum this volume element from z equal to 0 to, see, this is the plane z equal to 0 to z equal to 3. So you first perform the summation of this this thing. What is that? When you write what is that? Yeah, divergence of A into d tau means, as I said before, divergence of A into d tau here, the one I put a tick mark here. Divergence of A into d tau will simply measure the net outflow of the vector field A from this volume element. The net outflow of the vector field A from this volume element. So if you do the summation of the volume element, the net outflow of the vector field of each volume element, you assume that there is another volume element just below this, and below that there is another volume element, and above this there is another volume element, above this there is another volume element, like that. From z equal to 0 to z equal to 3, you can have very large number of volume element. You assume that there are large number of volume element here from z equal to 0 to z equal to 3. So the divergence of A into d tau simply represents the net outflow of the vector field from this volume element. So by integrating from z equal to 0 to z equal to 0 to z equal to 3, we are summing up the divergence of A from the bottom to top. We are summing up along this line. That is, we are forming this kind of rod here, the one I saw here in the figure. So this will simply sum up the divergence of A along the z-axis for every volume element, as you can see in the picture here. Now, after that, we have to integrate over x and y, because we are in addition to the z-axis we have x and y. So in order to integrate over x and y, we have to know that the relation between x and y is given by this, what is called equation of the circle here, x squared plus y squared equal to 4. So from this x squared plus y squared equal to 4, you simply write y as y square is equal to, I should have a pen, y square is equal to what is that, 4 minus x square. Y square is equal to 4 minus x square. And when you take the square root, y is equal to, square root is always plus or minus 4 minus x square. So 4 minus x square. So you have to perform summation over y from minus of square root of 4 minus x square to plus of 4 square root of 4 minus x square. And then you have to integrate over x from, what is x value here at this point? At this point, x value will be plus 2. Because why is that? Because the radius is 2. So if you go to the back side here, what is x value at this point? X value is minus 2. So if you perform the integration like that by choosing the limit, if you have to integrate over area of a circle, then this is how you have to proceed. Y, you just take it as minus of square root of radius square, r square minus x square, to plus of that. And then you integrate x from minus of array r to plus of r. Yeah. So if you follow this integration step here, like the one shown here, you work out every step yourself, because this is the part you have to play here. First, you have to see the first integration with respect to z. So first integrate this function, this whatever quantity here with respect to z. Then you will get 4z minus 4yz plus 2z squared upon 2. Then you put the limit of z as 0 to 3. then put the limit of z as 0 to 3, then this is what you will arrive at. And then after this, again integrate this function with respect to y. So the second integration is with respect to y, so integrate with respect to y and then put the limit, then you will arrive at this. And then after that you integrate with x equal to -2 to +2, then you will arrive at see the next is integration of this with respect to -2 x with respect to with respect to x from -2 to +2. So what we have to know is that you are integrating from minus quantity to plus quantity, to plus quantity. You have to consider what kind of function we are integrating here. Here you see that this is this quantity is an even function. What is an even function? Even function is a function where f of minus of x is equal to f of plus of x. So you take f of minus of x, this is your fx expression here. F of minus of x will be 42 times square root of 4 minus x, you just put it as minus of x whole square here. Minus square is plus, so minus x square. So this is same as your f of x. That means even if you go to the negative side of the limit, it will be same as the positive side of the limit. F of minus x of x equal to fx. If you take any function here in which f of minus of x is equal to minus of f of x, this is called odd function. This is in the case of odd. Okay, in the odd function, f of minus of x is equal to minus of f of x. So if it is an even function, the normal rule of integration is that whatever you integrate on the negative side of the x-axis will be same as whatever you integrate on the positive side of the x-axis. So if fx is an even function, minus of a to plus a of f of x will be 2 times 0 to a of f of x integration. Okay, so that is the property of an even function. You have to use that property. And here after that you write this as like this, 2 times square root 0 to 2 for the integration from 0 to 2 for the 2 square root of 4 minus of x squared dx. So in order to integrate that, we again use what is called trigonometry here. Trigonometry we are going to use is we just put x equal to 2 sine theta, then dx will be 2 cos theta d theta. You just differentiate this equation. Dx will be 2, differentiation of sine is cos theta, 2 cos theta d theta, right? Then you know that at x equal to 0, so here the integration limit is now using this even function property, the integration limit will be, instead of -2 to +2, we have to integrate from 0 to 2. So the lower limit of x is 0, the upper limit of x is 2. So at the lower limit, that is x equal to 2, what will be your theta value? Theta value can be deduced from here. Sine theta, from this relation, you see that sine theta is x upon 2. So when x is 0, sine theta is 0. Sine theta will be 0 only when your theta value is 0 degree. So what is the upper limit in terms of this new trigonometric function? So the upper limit in terms of x was 2. So as I said here, instead of -2 to +2, we are now converting to 2 times 0 to 2. So the upper limit is 2 here for x. The upper limit is 2. Then if you put in this relation here, sine theta equal to x upon 2, the upper limit as 2, then your sine theta is 1. So when do you have sine theta as 1? Sine theta will be 1 when your theta value is pi upon 2. So instead of writing the integration with respect to x-axis, we can simply convert the integration with respect to theta here, d theta here. So here you see that dx is equal to 2 cos theta d theta. So instead of dx, I will simply write 2 cos theta d theta. And instead of x, we write 2 sine theta. That means square root of 4 minus 2 square is 4 sine square theta. And the limit also changes from 0 to 2 to 0 to pi upon 2, 0 to pi upon 2. So yeah, this is a like here you can take 4 as a common factor. Square root of 1 minus sine square theta will be your cos theta. So you can have 2 cos square theta. So 2 cos square theta. So you can convert cos square theta as like this. You can see that cos square theta is actually 1 upon 2 plus cos 2 theta upon 2. So if you use these trigonometric relations, you can continue the integration as shown here. You work out all the steps here. Then finally, the volume integration will be 84 pi. Now, in order to verify the divergence theorem, we have to see that the volume integration of the divergence of the vector A over the whole volume equals the surface integration of the vector A over the whole surface. So here you see that on the right hand side there is a surface integration of the vector field over the whole surface S. And as I already explained, the surface enclosing the volume can be divided into 3 sections. The first surface S1, the second surface S2, third surface S3. So I think I have already identified the surface here. S equal to 1 is the circular surface at the bottom. S equal to 2 is circular surface at the top. S equal to 3 is the curved surface here of the cylinder. So here you see that at s equal to 1, the equation of the surface is z equal to 0. For every point on the surface S1, the z value is 0. And here ds vector here means ds1 into n cap. What is n cap here? Here your ds vector is equal to, wait, I don't have to write because I don't have a pen. This thing here I have already written right here. ds, for every surface integration, your area element vector ds vector is equal to ds into n cap. n cap is unit nor vector normal to the surface area ds, unit vector normal to the area element ds. Okay, so whenever we take the normal, we have to take outward unit vector. Okay, here remember n cap is an outward unit vector here. Now on this surface S1, you just assume there is a small surface element here like this, the one I draw here. If you can see, this small surface element is what we define it as your ds1. Now what will be our unit vector? Your unit vector n cap is always outward normal, unit normal vector. So what is the outward direction? Outward means outward from the volume. So your outward direction will be downwards like this. Your outward direction will be unit vector. Your outward, your n cap here will be unit vector pointing outward from this volume. So this is a flat surface on the xy plane. So the n cap will have to have a direction along the negative z-axis. If you look at this picture here, your n cap will have a direction along the negative z-axis. So here your n cap will be, in this surface, your n cap will be direction along negative z-axis, means unit vector along negative z-axis will be minus of k cap. But if you look at the surface S2 here, on the surface S2, just assume that there is a surface element, something like this. This is your surface element, your ds2. This is surface element of S2. This is your ds2. So on ds2, what will be the outward unit normal vector? outward unit normal vector will have to be a unit vector normal to the surface, pointing away from the surface. So the pointing away from the surface will be something like this. This will be your n cap in this case. This will be your n cap in this case. So your n cap here will be equal to k cap, because n cap here is pointing along the positive z axis. Yeah. So remembering that, you can continue the calculation here. At z is equal to 1, z value is 0. So normal vector to the surface will be here. I think we have discussed, I don't know if I have discussed this gradient. Okay, there's one problem here. Maybe I skipped that. I don't remember discussing that. Just where is that? Where is that? Where is that? Oh, I skipped that part. Okay, later on, maybe in the class, I will discuss that. So what I was trying to tell you is that if you have any surface, the equation for this any surface can be represented like this. Phi is equal to constant c. Phi equal to constant c. Phi is a certain function of, phi can be a function of x, y, and z. Phi can be a function of x, y, and z. Phi can be a function of x, y, and z. Now, when you take a gradient of phi, this gradient of phi, this is there in my notes. You can see that also in my notes. Gradient of phi will always represent a vector normal to the surface represented by this equation. A vector normal to the surface represented by this equation. If you want to find out the unit vector normal to the surface, what you can do is you can divide this grad phi by its magnitude. If you divide a vector by its magnitude, then you will get unit vector along that particular vector. You will get unit vector along that particular vector. So here, phi, instead of phi equal to c, surface S1, the equation of the surface S1 is z equal to 0. So you just take your phi as, here your phi is simply z, and your constant c here is 0. Your constant c here is 0. So in order to find the unit vector perpendicular to the surface, you can also take the gradient of z, Okay, the gradient of phi or gradient of z. Gradient of phi or gradient of z will be simply k cap here. But as I was saying, we have to consider outward vector. Outward vector here in this as z equal to 0 surface is unit vector pointing downwards, that is along minus k cap. So this is your unit vector here is k cap. And your a vector, in your a vector, what was your a vector? Your a vector was 4x I cap minus 2y square z plus z square k. And on the surface z equal to 0, z value is always 0 for every point there. So you simply put z equal to 0 for the bottom surface. The bottom surface S1, for bottom surface S1, z value is always 0. So your a vector here is this, because for every point on the bottom surface, z value is 0. Then when you take the dot product a vector dot n cap, your n cap is minus of k here. So I cap dot k cap is 0, j cap dot k cap is 0. Therefore, this integration or the flux of the vector field across the bottom circular surface will be 0. The bottom circular surface will be 0.